Hi, so I'm David, and this talk is about good quant LDPC code with linear time decoder. So this is the work with Irit Dinur, Min-Hsiu Hsieh, and Thomas Vidick. So we'll be mainly talking about quant LDPC code, and this talk will take a more abstract view. So we'll think of it as bounded degree three-tiered chain complex, and let me explain what this is. So a three-tiered chain complex consists of three vector spaces, f2, x0, f2, x1, and f2, x2. So they're generated by sets x0, x1, and x2. Furthermore, we have these linear maps delta 0 and delta 1 that compose to 0. So these maps are called the co-boundary operators. And if we take their transpose, these partial maps, they're called the boundary operators, and they compose to 0. So the vector spaces together with linear maps, they're with this condition, it's the chain complex. So for bounded degree, it's saying that these maps are sparse, meaning that there is a constant number of ones on each row and each column. So two most important parameters for code is dimension and distance. And for dimension k, it's the dimension of the homology, which is the dimension of the kernel minus the dimension of the image. For distance, it's the minimum of the x distance and the y and the z distance, where the x distance is the minimum weight of the vector inside this x1, f2, x1, which is in the kernel, but not in the image. And dz is defined in a similar way, but it's using the partial maps. And so for those that are familiar with high dimensional expander, these are also called the systolic and co-systolic distance. So in our work, we also talk about decoders, but I won't have time to go through them. I just want to say that there's also a way to define them using chain complex languages. So the main question of this talk is that, are there quant LDPC code with linear dimension and linear distance? And does this code have linear time decoder? So the first question is also known as the question of whether good quant LDPC code exists, and it's only solved in 2021. So that brings us to the history of these quant LDPC codes. So the first quant LDPC example is this Torah code, which has square root distance. So recall n is the number of qubits. So it has square root distance and dimension 2. So soon after, this dimension is improved to linear to n. So that's the optimal possible. But the distance is only improved by at most a polylog factor. It was until this fiber bundle code in 2020, which breaks the square root barrier. And soon after, there are more works following it. And in 2021, by Palantis and Kalachev, they resolved this good quant LDPC question. And after that, there are many more papers that follows. So in particular, now we know that there are 3 code constructions. And we know that they have linear time sequential decoder and log time parallel decoder. In particular, I want to highlight that there is independent of quantum codes, there is work on locally testable code. So classical locally testable code that actually shares a lot of similarity to these quantum code constructions. And in fact, our work, many of our proof techniques actually follows from that work. So these are some results on the coding theory side. But there are also applications in other places. So for example, there's a question of, okay, what's the optimal code one can construct with the geometrical constraints? So meaning that the check should only interact with geometrically locally nearby qubits. This was solved, the gap was closed to Polylog recently in this work by Portnoy. And one key ingredient is these good quant LDPC codes. So outside of coding theory, there are also applications on some hard instance for sum of squares and also the NLTS conjecture. Okay, and let me just summarize our main contributions. So first, we construct a new family of good quant LDPC codes which we show they have linear time decoder. And in this proof, we also show a key lemma, which gives the optimal parameter for robust tensor codes. So we'll say more about that later. But for now, you can just think of it as a GV bound for tensor code. So usually GV bound only applies to one code, but here it's a tensor of two codes. So these are some concrete results, but more conceptually, our proof is arguably simpler, and the reason is that we rely, we are able to use the stronger robust codes, so that simplifies the proof. And alternatively, for people that thinks about higher dimensional expanders, in our paper we tried to phrase our proof and results using this language, and in particular we use the notion of boundary and small set boundary expansions. Okay, so now let's dive a bit deeper and talk about the construction. So in fact, the construction is quite similar to the classical expander code. So just a quick reminder, to construct a classical expander codes, the strategy is to combine a Cayley expander graph with a code of large distance. And we combine them using the Tanner code construction. So in quantum, it's similar, but there is a sense that in quantum, it's two-dimensional. So in fact, we have to take a two-dimensional graph with two codes, and for the code we have to take two codes, and the distance condition now becomes this robustness condition. So by taking these two ingredients, we can combine again using Tanner code, and that's basically the construction. And alternatively, this robustness condition can be rephrased as this boundary high dimensional expander, this condition. So, and when you combine with the graph, you get a small set boundary and co-boundary expansion. So that's essentially what implies all these results, including sum of squares, NLTS, and linear distance. And in fact, recently we also learned that this also implies linear energy barrier. So let's review each component. So first, let's start with the graph. So we have to construct the Cayley graph, we need to have a group and two sets of generators. We also require this Cayley graph GA and GB to be expanders, so lambda expanders. So from these, we can construct several objects. This includes vertices, edges, and faces. Start with the vertices. So particularly, we have four groups of vertices. So each group is a copy of the group. So essentially we have four groups, and they're labeled by 0, 0, 0, 1, 1, 0, and 1, 1 to indicate their position. And then we have these edges. So for example, the vertical edges connects G with AG, and the horizontal edges connects G with GB. And because the left and right action commutes, these edges actually form squares. So for example, G, AG, GB, and AGB, they form a square. Another way to think about these graphs is through the local view. So we focus on an horizontal edge and look at what is the neighboring objects, then you can see that's connecting to delta number of faces because they're delta choices of A. And instead if we focus on a vertex, then there are delta choices going down and delta choice go horizontally. And notice that each pair of horizontal and vertical edges forms a square. So there are delta square number of faces. This local view would be important later to construct, to do the Tanner code construction. So that's a graph. Then we'll have to talk about this tensor code. So to get a tensor code, we first start with two classical codes where MA and MB are the generator matrix. So we can take the tensor product with the identity to form these four maps. So MA tensor identity and identity tensor MB. It's easy to see that these maps commute, and so they actually forms a chain complex. Okay, and so the robust condition on this tensor code is essentially the call boundary expansion, which says that for each vector, for each purple vector, after applying this delta map, it expands by a factor of d2. And it's true up to this delta 0c0 map, this vector, which is the boundary. So what that means is up to some boundary, the vector expands. And so for those who's the first time hearing this concept, we just want to point out that this in one dimension, this corresponds to the distance. And this is why I say robustness is a generalization of the notion of distance. I wanted to go into the detail, but you can see the similarity here. So D1 is the code distance in the classical code, and D2 is the robustness parameter. Okay, and so the key lemma is that there exist two classical linear codes, MA and MB, such that MA tensor MB, so this chain complex, and also this MA perp tensor MB or perp, these both chain complex has co-boundary expansion with linear parameters for D1 and D2. And it's a good time to digress a little bit and talk about the small set co-boundary expansion. So here is the definition for co-boundary expansion. And for small set co-boundary expansion, we basically include this additional property that instead of saying that all vectors C1 has to expand, we only require C1 with low weight to expand. So if it has weight less than alpha times x1, then it has to expand. Yeah, here we include another parameter gamma just for completeness. And in particular, these alpha, beta, gamma, all of them has some corresponding code notions. So for example, alpha corresponds to distance, beta will correspond to energy barrier, and gamma will correspond to the soundness of the classical locally testable codes, which we'll not talk about in this talk. Okay. All right, but let's come back to the main story. So we previously have the graph and then the code. So now we're going to combine them using the Tanner code construction. So the idea of the construction is that we'll split each of these vertex and edges. We'll split them into multiple copies, and this is determined through the structure of the code. So for example, we can so here we'll start with this graph, and so first recall that we have this local view around a vertex, and recall that for each pair of vertical and horizontal edges, we can form a square. So that's why we can organize them into this grid. Next, we'll split each vertex into a grid of vertices and each edge into like multiple edges. So after the splitting, these points become these blocks. And finally, we can define the maps between them using these, using the code, using the tensor code. Yeah, so essentially what happens is these points split into multiple things, and then they're connected based on the structure of the code. Later on, we'll use the same graph to represent this, the code after Tanner construction. Okay, so now we have this graph, and the last thing to do is to turn that into a chain complex. So in fact, there are multiple ways of doing it, and previously I mentioned there are three methods of construction, and this is a place that they differ. But let's first focus on our construction. So what we'll do is that we would map each vertex into x0, each edge into x1, and then each faces into x2. Yeah, so essentially they correspond to x checks, qubits, and then z checks. And notice that they're organized by dimension. So when I just discuss this one on the right. But besides this assignment, there are also other choices. So for example, we can say, okay, the horizontal edges correspond to the x-check, the vertices and the faces correspond to the cupids, and then the vertical edges correspond to the z-checks. Or we can say, okay, the vertices correspond to the checks and the faces correspond to the cupids. Yeah. So there are different benefits for these constructions. In particular, for the first two, they're symmetric, meaning that if we flip the chain complex, meaning we switch x and z, essentially the construction is the same. So the edge maps the edge. And what this means is that if we can show expansion in one direction, the other direction just follows immediately. So we essentially don't have to prove in one direction. But for us, our construction is not symmetric. In particular, these x-checks correspond to 0-dimensional vertices, but z correspond to these faces. So what that means is that we'll actually have to show expansion in both directions. Nevertheless, this choice has a benefit in that our construction is organized by dimension, and when we want to go to higher dimension, it's easier to think about their generalizations, as we'll comment at the end of the talk. Okay, so that's the construction. Now we'll quickly go through the proof. So the proof, as I said, we have to show two directions. So for the forward direction, we'll show it by using the expansion property of the graph and a code. For the reverse direction, what we'll do is we'll reduce this problem into the question of co-expansion. Okay, so that's the two parts. So the first part, the proof idea is using these random, you can think of it as using random walk. And there are two kinds of random walk that we look for. One is using the local view around an edge. So this edge, we can walk to these three types of edges. And another type of random walk is through this local view around a vertex. And so now it will be these edges, these blue edges mapped to these other blue edges. And essentially, after we work out the details, what you found is that if your choice of local code and your graph satisfy this inequality, then the full construction, the standard code, has small set boundary and small set expansion. I noticed that this condition is quite similar to the Tanner code, namely that we want the distance of your local code to be large enough. Okay, so that's the first part. For the reverse direction, what we want to show is that given these vectors on these blue and red vectors, which map to 0, we want to find these orange vector. And the strategy is similar to like decoder, where we reconstruct multiple objects. And this full proofs only requires linear algebra. Okay, so how do we find the orange part? So we can first solve it locally on the 4 corners. However, they might not agree. And so the next question is to try to match them together. Okay, so we only have to focus on their difference. And we can use the duality between parity check and generate to turn them into another question. And turns out that this question is precisely the question for asking whether it has co-expansion. Okay, and because our previous result, we know that, okay, they indeed have co-expansion, and we can solve these green regions. Now we can map them back to get these alpha, beta, gamma, and delta. Okay, so overall what happens is that we found these alpha, beta, and gamma, delta, and turns out they're precisely the matrices that the additional matrix, additional vector you should add to A, B, C, D to turn them, to match them together. Yeah, so now you find this question mark and then you're done. So in the paper, we also study these decoder, and essentially it follows the similar strategy. Okay, so just to summarize, the construction is based on combining a left-right K graph and a boundary high-dimensional expander to get a small set boundary encode boundary expander. And this can be used to imply a lot of results. So what are some open questions? Well, one question on the coding theory side is, so here we focus on constructing the code. But one question is, can we turn them into some robust computation? So that's fault tolerance. And outside of coding theory, one can ask, are there other applications? And at the end, I want to back to this question of higher dimensional generalizations. So in particular, it's a natural question to ask whether there is a high dimensional generalization, but at the same time, it has some practical implications on quantum locally testable codes. So again, what we need here is an expander, but here it has to be 4-dimensional. So a OK candidate are these abelian Cayley expander graph, so they're somewhat optimal up to some polylogs. The real challenge is to construct these tensor codes, these robust tensor codes. So in particular, in 2D, we have this proof that can show the existence of these expanders, these robust codes. However, they rely on the notion of rank, which doesn't generalize in higher dimension. And so this is really the bottleneck. But suppose you have both of these ingredients, then our proof technique can combine the two and then gives you a locally testable code. Okay, and so that's the end of the talk, and thank you.